I want to open the resulting executable file with a hex editor, just to understand how the data structure looks like, how the data section resides inside the PE. And I think that it is pretty interesting. I already said it, and I will say it again. Whenever you do some major modification to your executable file, it is an interesting experiment to see what has changed. It will make you a much better programmer. So let's take a look. We first save this file. Maybe earlier we will change the value 0 here into something else. I remind you that this number 0 is the initialization value we put inside those 5 D words. Basically, those 5 D words begin with the value 0. This is something which is going to be hard to find inside the executable file. We've already seen that executable files are full with zeros. Maybe you can put some other number. For example, 1, 2, 3, 4, 5, 6, 7, 8 in base 16. This number will be much easier to find. Let's save this program. And now we are going to assemble it. Good, assembly went okay. Let's open it with Hex Workshop. As usual, the portable executable or the executable file begins with MZ, and then we have this interesting string. This program cannot be run in DOS mode, and so on. Let's hunt for this number 1, 2, 3, 4, 5, 6, 7, 8. This file is not so big, so it will not be a very big problem to find. And we find it here. Maybe surprisingly in the reversed byte order. How can we know that this is really the one? We could be pretty sure because we have exactly 5 D words here. And all of them are 1, 2, 3, 4, 5, 6, 7, 8. Maybe in the reversed order. You might be wondering how come the number is in the reversed order. We didn't put it in a reversed order. We asked for 1, 2, 3, 4, 5, 6, 7, 8. And we got instead 7, 8, 5, 6, 3, 4, 1, 2. Definitely not what we wrote. Let me explain. There is a convention in the x86 architecture to keep memory in this fashion. It is called the Little Endian convention. In this convention, the most significant byte of the D word, and in this example it is 1, 2, is kept last in memory, or maybe in the highest address. This convention is called the Little Endian. We are going to talk about it a bit later, but for now, just make sure that you understand that whenever you write a program and you put something like this in memory, for example a D word, it will be written in the reversed order, and you should not be surprised about it. If we are already here, let's take a look at the code section, just to make sure that we can find it. A good guess would be to say that it begins here. As we can see, it has a very nice beginning address, which is 400. And it contains really strange numbers, which is about what we expect from code, from x86 code. By the way, if we take a look at the data section again, we can see that it also begins at a very nice address, 200 in base 16. I want to show you another example which is related to this one, and I think it is pretty important. It is called reverse constant.asm. Let's take a look at the source code. Basically, it contains about the same source code which we have seen inside reverse.asm. And it also pretty much does the same thing. However, there is some difference. We have this line which says amount nums equals 6, which we didn't have before. This is what we call a constant definition. We define some constant or some name to represent a number. Then we can use this constant just like we use any usual number. As an example, let's see where it shows up in the code. It shows up in a few comments, but I really care about the code lines where it shows up. The first one is here, in this data declaration. We also have it here, move ECX amount nums. And also here, move EDI amount nums. I want to compare it for a moment with the previous program, reverse.asm, just so we can see the differences. As you can see, this number 5 was replaced by amount nums, and also this number 5 was replaced by amount nums. Also in this location, dd5 dup and this number 5 was replaced by amount nums. I want to explain a few things about this constant and this idea of constants. First, you might be wondering, who does this work of turning the constant into a number and so on? Does the processor have some really special feature of understanding constants? Well, this is not the case. The processor doesn't know about constants. Translating the constants into numbers is something that the assembler does. Constants are really for you. They help you write better code, and they help other people understand your code. This is some kind of a gift that you get from the assembler. The assembler, just before turning your text into binary, is going to replace every place where you put amount nums with the number 6 in this example. Which means that the constant translation is something which is done at assembly time. It happens at the time when you assemble your program, not at runtime. I want to explain why would you want to use constants. Because we've already seen that the previous example worked just fine. So why would we want to add this kind of line to our source code? Let me explain. We've already seen that the number 5, for example, in reverse.asm shows up a lot. What if we wanted to handle more numbers? Maybe 6 or 7. We would have to change many lines. We would have to change this line, and also this line, and finally this line. Imagine what would happen if this would be a very large project. We would have to search the number 5 in all of our source files. Further, imagine what would happen if we forgot some place. We would have to deal with really strange errors. It would be so hard to make it work right. On the contrary, if we use a constant, our life will be much easier. At this point, if I want to change the amount of numbers that the program can deal with, I can just change this line, only one line. I can change it, for example, to 3, and I'm going to get the correct behavior. I don't have to search through all the source files and change everything. Let's assemble and run this program just to see that it gives us the correct result. First I save the program, and now I'm going to assemble and run it. I remind you that this time the program expects exactly 3 numbers. I will give it the 3 numbers 3, 2, 1, and as a result, as expected, I get 1, 2, 3. Exactly the numbers that I gave the program, but in the reversed order. Just as a conclusion, make sure to write your programs so that they will be easier to change in the future. I don't say to overdo it. You don't have to think about anything that could happen. But think a little ahead. Always make sure that if you wanted to change something, even a small thing, you would be able to do it easily. In this example, we just used a few constants. We replaced some numbers with one constant, and look how it made my life easier. I can just change this number to anything that I want. Maybe I want 100, and it is so easy. This is what I wanted to show you about constants and also about memory access.